In electricity magnetism. In this video, we're going to look at what happens when we have current carrying wires, okay, in a magnetic field. In the previous video, we looked at moving charges. Now let's look at what happens when that charge is now inside of a wire. All right, so one thing to recall is that the uniform magnetic field will exert a force on a single moving charge. But remember, wires contain bunches or a bunch of moving charges, thus creating a current inside. All right, so to determine the force, right, the magnitude of the force that the wire will experience when placed in a magnetic field, it's going to be F equals IL cross B. Okay, so where I is the current, L is the length of the wire, and B is the magnetic field strength. Okay, but we to get rid of the cross product, right, to remove that, we just simply add that sine theta again. Okay, so this also shows us the importance that these factors, L and B, right, are full strength when they're perpendicular to each other. Right, because then your sine of 90 is 1. All right, and now again, so we talked about in the last video, we talked about right-hand rule. Well, this also has a right-hand rule. Sorry. Okay, so the right-hand rule applied here is our thumb is going to be in the direction of the current, our fingers are going to be in the direction of the magnetic field, and our palm again will show the force. Okay, so current, magnetic field, force. Okay, so you can see that here in this little diagram. Okay, you have thumb in the direction of the current, fingers in the direction of the magnetic field, and our force in this case would be out of that plane. All right, now you can place that current carrying wire inside or in between two magnets. Okay, but you follow the same thing. You can see right here is how the force would be experienced. So remember, magnetic field goes from north to south, right? So it's coming across this wire like this. So I'd put that in the direction. My current at that point, okay, here coming around in this little circuit we have here is going down. So magnetic field to the right, the current down, right? And so the force would come out of the page. You can see right here, the F is coming out of that page. All right, so here are just some examples, okay, of using this right-hand rule. So in A, so we use our right hand again. Magnetic field is our fingers, okay? Current is our thumb, right? So fingers out of the page. It's like I'm looking at the tip of the arrow. The current's going to point down, which means my force is my palm, right? And so my force would be here to the left, right? So for A, the force would be to the left, okay? Now let's look at B. So again, magnetic field is fingers, current is my thumb, my palm is facing what would be into the page. Right, so if I'm going to draw it on my diagram here, I'd be looking at the feathers of the arrow. Okay. C, again, magnetic field, current, right? So magnetic field, current, my force would be going up. Okay. D is very easy. Well, I can't arrange my hand in such a way to get these two, right? I'd have to like bend my thumb all the way back. But what does that mean? The force, right, would be equal to 0, right? Why? Another reason why. They're 180 degrees to each other, right? What's the sine of 180? What's the sine of 0? That's going to be 0, okay? E, so magnetic field, current, right? My finger, my palm points to the right. Okay, and then the last one, finger's magnetic field, current is coming out of the page, pointing at me. And so that means that my force, direction of my force would be down. All right, so let's look at an example using our direction, but then also using our equation to calculate. So here we have calculate the magnitude and direction of the force on the wire shown in the figure, given that B is going to be 1.50 Teslas, L, the length inside that magnetic field, is going to be 5 centimeters, and I is going to be 20 amps. Okay, so I can use my equation, F equals ILB sine theta, but you can see here B is going across, I is coming through, so they are at 90 degrees to each other, so sine theta is just simply going to be 1. So my magnitude is just going to be given by ILB, okay? So it's going to be 20 amps. The length you must convert to meters, and then our Teslas, our magnetic field strength is 1.50. Okay, interesting enough, this is just also equal to 1. So the magnitude of my force would be 1.5 newtons. And so let's find the direction. Okay, so fingers in the direction of the magnetic field, thumb in the direction of the current. My palm again represents the direction of my force. So this is going to be in the positive y direction, or we just can call it up. Okay, so again, it's a very simple calculation. Now, the next thing we're doing is we're going to take it one step further. What happens when now I have, the whole wire into that magnetic field? How does that affected by looking at the torque, right, on a current carrying wire?